In item 3, we've got one of those graphs that we're very familiar with. It's made up of line segments and a piece of a circle. And we get this all the time on questions where we're going to be evaluating integrals geometrically, right? And those areas that are bounded by lines and semicircles, we're able to do that. All right, so in question A, they tell us that if we integrate this function from -6 to 5, that we get a total of 7. All right, and so what they want to know is what is the value of the integral from -6 to -2. All right, and we know nothing about the graph from -6 to -2. The graph cut off at -2, and we don't know what happens over here. Okay, so our plan of attack here is that since they told us what you get when you integrate from -6 to 5, and we can figure for ourselves how much area you get if you integrate from -2 to 5, since we have the graph, then using those two numbers we can figure out what is the value of the integral from -6 to -2. Okay, so what we need to do is figure out what we can calculate, which is how much we get when we integrate from -2 up to 5. In other words, the piece of graph that they gave us. All right, so let's see. From -2 to -1, we get this triangle here. But then from -1 to 0, we get a congruent triangle that's below the axis. So these two triangles just cancel each other out, right? One will be positive area, one will be negative. And the same thing happens between 0 and 1. Now you can't see it in my rough sketch here, but the little triangle below the axis and the little triangle above the axis there are actually congruent to each other, and so they also cancel each other out. So we don't need to start counting area until we get to 1. Okay, so this integral is actually equal to the integral from 1 to 5. Because from -2 to 1, all that's going to be 0 because the positive and negative areas will cancel out. All right, how much area do we get from 1 to 2? Well, between 1 and 2, you get 1 whole unit, and then the triangle up here cuts 2 units in half, so that's another unit. So there's 1 unit up there and 1 unit there. That makes 2. And then we got this area under the circle. And to get the area under the circle, we're going to take this whole square right here, this 3 by 3 square, and we know that its area is 9. And we're going to subtract the area inside that quarter of a circle. All right, that is 1/4 of a circle that has a radius of 3. Right, here's the center of the circle is at 5, 3. Here's the radius of 3. And what is the area of a circle with a radius of 3? It's pi times 3 squared. And we want to take 1/4 of that because that's only 1/4 of the circle. Okay, so when you integrate from 1 to 5, you get 2 units in here between 1 and 2. And then from 2 to 5, we take this whole square of 9 units of area and we subtract what I shaded in here, that 1/4 of a circle. And so that should leave us with the area that's underneath here. All right, so that gives us 11 minus 9 pi over 4. Okay, so we can now put that together with our other facts. We know that if we integrate from -6 to 5, that would be the same as integrating from -6 to -2 and adding what we get when we integrate from -2 to 5. Right? This is one of our definite integral properties, right? And which of these 3 things do we know? Well, they told us this first one is 7, And this minus 6 to minus 2, that's what we're looking for. And this last one here from minus 2 to 5, that's what we just figured out. Okay, so the entire area of the whole region is the area from minus 6 to minus 2, plus the thing in parentheses here is the area from minus 2 to 5. And so we just do a little algebra to solve there, right? We subtract this thing in the parentheses from both sides, and that tells us that from minus 2 to, from minus 6 to minus 2, we've got 7, take away 11, that's negative 4, and then we're going to add 9 pi over 4 to both sides. So there is the area or the value of the definite integral over the part of the graph that we can't see. We don't have that piece of the graph. Now, I did all of this in exact terms. You could have used your calculator and done decimals here, but of course they had the question set up so that you should be able to do it without a calculator. It was a non-calculator question, but you know, since we're using the calculator this year, I think there wouldn't be anything wrong with just doing this with a calculator. All right, let's look at part B here. They want us to evaluate this rather messy looking definite integral here where we're integrating 2 times f prime of x plus 4. And remember a while ago I talked about how this line right here, this is one of our definite integral properties, right? That if you integrate from a to c, it's the same as integrating from a to b and from b to c and adding those up. All right, that was one of our definite integral properties. And another one of our definite integral properties was the way we could split up an integral by splitting up the sums and the products. So let's see, I'm going to split this up into the sum of 2 integrals. I'm going to integrate this piece and integrate this piece separately. And when I integrate this first piece, since 2 is a constant, it can come outside. All right. So there's integrating the first piece, plus we'll integrate the second piece of that. All right, so integrating 4, that should be easy, no trouble there. Integrating f prime, let's see what's going to happen when we integrate f prime. Well, if you integrate f prime, its antiderivative is just f. And by the fundamental theorem, we need to evaluate that from 3 to 5. And what about integrating 4? Well, that's the area under the graph y equals 4 from 3 to 5. Well, that's just a rectangle, right? That's a rectangle that's 4 units tall and 2 units wide, so that's 8 units. Okay, so this integral here is a simple geometric integral. All right, what do we get when we integrate f from 3 to 5? Well, it gives us f of 5 minus f of 3, right? That's how the fundamental theorem works. You plug in the top number and subtract what you get when you plug in the bottom number. Now, how are we going to get f of 5? Well, we got the graph of f. So let's just look on the graph of f and see what f of 5 is. You can read off of the graph that f of 5 is 0. And f of 3, you couldn't read it off the graph, but they told you that f of 3 is 3 minus root 5. That was actually in the instructions that we know there's a point on this graph at 3, 3 minus root 5. So that's the value of f of 3. All right, so let's see, what's that going to give us? We're going to have 2 times negative 3. That's negative 6, plus this 8 out here makes 2. And we've got the opposite of negative root 5, so that's root 5 times the 2 out front makes 2 root 5. And so there's the value of this integral. Okay, so we had to use the properties of an integral to split it up. And then we had to use the second fundamental theorem to evaluate this one and read the values off that we needed for this calculation from the graph. All right. Now in C, we're looking for where G has a maximum. Right? And G is defined to be this definite integral from -2 to x. And the function that we're integrating here is function f. So it's the area under the graph of f from -2 to x. That's what you get when you plug x into this function. All right, and we want to know, where does this have a maximum? Well, if you want to know where a function has a maximum, you need to know how its derivative behaves, right? You need to know things like where the derivative is 0, where it's positive and negative. And so we need the derivative of g. So let's remember that we've got a rule. It's called the first fundamental theorem of calculus. And it says that if you take the derivative of a definite integral function where you're integrating from a to x, some function f of t, that you get f of x, right? That's the first fundamental theorem of calculus, or depending on which textbook you're looking at, they might call that one the second and the other one the first. But at any rate, it's part of the fundamental theorem of calculus that this is what you get when you take the derivative of a definite integral function. So g prime is the derivative of this definite integral function. And so, using the first fundamental theorem, plop, there it is. G prime is the same thing as f. So that graph that we got up there at the top of the page is not only the graph of f, it's also the graph of g prime for some function g that we don't really know a whole lot about. Right? But we do want to find out, where does g have a maximum? So we need to set the derivative equal to 0. Let's see where this thing is 0. Well, this is the same as saying, where is f of x equal to 0? And where is f equal to 0? Well, if you check out the graph, you see it's 0 at -1. And then right here on my graph, it doesn't look like it, but on the one on the paper, you can see that it's at a half. Right? This graph crosses the axis at -1 and at +1/2. Right, so let's do a sine line now. We're interested in where it has a maximum between -2 and 5. And we're going to put our -1 and our +1/2 on the number line, because those are places where the derivative is 0. And let's put some signs in here between -2 and -1. Remember, this is the graph of the derivative, so between -2 and -1, it's above the axis and it's positive. And then you can see on the graph that between -1.5, that's where the graph of f, which is g prime, was below the axis, so it's negative. And then at 1/2, it crosses over the axis and stays positive. So what are our candidates for where the maximum is going to occur? All right, so this graph is increasing and then decreasing. So we could have a maximum at -1. Now at 1/2, that's where there's going to be a minimum, right? Because it's decreasing and then increasing. And this can be easy to forget, that since over this interval from 1/2 to 5, g is always increasing, it could be that the absolute maximum occurs at 5. Okay, because coming up to 5, it is increasing, so that could very well be the highest point on the graph. Or it could be here at -1, where it switched from increasing to decreasing, and so had a maximum there. We need to know which one is the biggest because we're looking for the absolute maximum. So we need to calculate both of these values and see which one's bigger. All right, so what is g of -1? Well, how was g defined? G was defined to be the definite integral from -2 to x, but in this case we plugged in -1 for x. And how do we work out this integral? Well, we've got to go back up here to the diagram and see what do you get when you integrate from -2 to -1. Well, you get this little triangle that's got a half a unit of area. So the value of g of -1 is a half. All right, let's do g of 5. We're going to integrate from -2 to 5 to get that. That's what g of 5 is defined to be. And I believe we already integrated from -2 to 5, didn't we? Somewhere up here. Yes, here it is. From -2 to 5, we worked that out, and what did we get? 11 minus 9 pi over 4. And if you approximate that with a calculator, 11 minus 9 pi over 4, you get about 3.931, and that's definitely bigger than a half, so that is the absolute maximum, or the absolute maximum. All right, in D, we're given what looks like just an atrocious limit. This looks like something that somebody made up when they were suffering an acute attack of indigestion or something. I mean, who in the world would have thought to throw in the arctangent function here? All right, so let's see. A lot of this hinges on what happens with that arctangent, because we need to know whether this fraction even exists when x is 1. All right, so let's look at that denominator and see what's going to happen. What's f of 1? Well, if we look at the graph up here, f of 1 is 1. That's easier to see on your real graph there. And how about the arctan of 1? When you plug 1 in there, what angle has a tangent of 1? Well, let's see. If you look at the 45, 45, 90 triangle, 45 degrees is pi over 4 radians, and the tangent of pi over 4 is 1, isn't it? So the arctangent of 1 is pi over 4. So this denominator is not going to 0. So this limit is not going to be a very difficult limit, because all we need to do is just plug the 1 in there. Okay, so we're going to get 10 to the 1 minus 3 times f prime of 1 over 1 minus pi over 4. Okay, so it's not, when I first saw it, I thought, oh, here comes L'Hopital's rule or something like that. But no, you don't need to worry about that, because this denominator isn't going to 0. So this can't be anything strange going on here. It's just whatever happens when you get to 1. All right, so the challenging part of this, well, other than that arctan, which might have thrown some of you, but, oh, but you got a calculator. Never mind, that's not even a big deal this year. Arctan of 1, calculator will spit you out a decimal for that at least. So f prime of 1, though, we do need to know what that is. And how do we get f prime of 1? Well, we look at the graph of f, and we ask, what's the derivative right here? Well, that point lies on a line segment with a slope of 2, doesn't it? Up 2 over 1, up 2 over 1. So the derivative there is 2, because that's the slope of the line there. So this is 10 to the first power is 10 minus 3 times the derivative at 1 is 2 over 1 minus pi over 4. So what's that? 10 minus 6 is 4. And if we get a common denominator on the bottom, that's 4 over 4 minus pi over 4. So that's 4 minus pi over 4. And so when we flip that bottom fraction over, we get 16 over 4 minus pi as our final answer there. And again, I'm working this out without using a calculator, but you won't be forced to do anything like that on this year's questions.